I'm Saptarshi Mukherjee. I'm working as an educator at an academy and CodeChef. This is a continuation of the interview preparation series which CodeChef is bringing to all of you. And this is our second session. I've seen you all have viewed my previous session, and the response has been quite interesting. So I hope that even this session shall be that much beneficial to all of you. So in this particular series, we are actually targeting such interview problems which are very, frequent in your coding interviews and placements. About myself, I am Saptarshi. I am a 6-star rated coder at CodeChef. I have been a master at Code Forces, and I have been a regionalist. That is, I have been to the ICPC regionals in 2019, and I'm going to join Google soon. That's about myself. So in these series, we are not targeting anything like competitive programming or some knowledge of data structures or anything. We are rather going to observe only those things which are pertinent for your placements and interviews, placement and internship interviews. So if you are appearing for placements, we expect that this will be a very beneficial session for all of you. In addition to watching these sessions, do let us know in the comments and in whatever channels you can about what other videos you are interested in, what other topics you are interested in. We are personally, I'm choosing 2-3 such important topics which are most beneficial and a bit non-trivial for your interviews. This is one of them. So we'll be covering the maximum area rectangle in histogram today. I hope you all will enjoy it, and yeah, now let's I think get started on it. And let me know, just like your previous video, how you have felt about this and how you'd like to have the next videos as well. Okay, cool. So maximum area rectangle in histogram. You can see this is basically a histogram which I have drawn in advance for you guys. This is basically what a histogram is. And when we say about maximum area rectangle, what we mean is, you can see this is a rectangle which is contained in a histogram. So this is a rectangle which is properly inside this histogram. But we will say that in case of this kind of a rectangle, which starts somewhere from here and ends up to here, this is not totally inside the histogram, because this is surpassing the limit at these positions. So when we say that we are talking about the maximum area rectangle in histogram, we definitely have to keep our rectangle within this limit. So this is the limit, and within these limits, which are denoted by their y coordinates, we actually have to keep our rectangle within it. So what are the rectangles possible? You can see from here that one such rectangle which you cannot stretch, which you won't be able to stretch, is something like this. You can say it can start from here and it can proceed like this and go up to here. After this, it cannot be reached. So you can say this is a rectangle. Now if I fix this width and this height, this particular height, we can say we cannot stretch it upwards beyond this, and we cannot stretch it downwards. Definitely we cannot stretch it downwards. We cannot stretch it leftward, because if I stretch it over here, then basically in this part my histogram is lying below the area that I am calculating. So I cannot let my histogram cover some additional area. I have to keep this histogram, or this rectangle, sorry, I have to keep this rectangle within my histogram. So I definitely have to abide by the boundaries that this histogram is given to me. So anyway, I think you're satisfied. This is one histogram which we cannot definitely extend. There is another histogram which I can show, that I can take maybe a smaller, we can take a smaller height, and we can show that I can proceed even better. So let us take this particular height, or let us take this particular height. From this height, I can say that I can proceed to a greater length. I can proceed through this entire length, and I can take this entire rectangle. So I can see these are two rectangles, one of whose height is greater, another of whose width is going to be greater. So which ultimately is going to give me the greatest L into B is what matters to me. This is the area. So there are many rectangles. You can even say that this is a rectangle, but you can say that this is a rectangle which can stretch at the top and as well as at the bottom, right? I hope it's continuing. Yeah. So from here you can say that for all possible rectangles, you need to find out the largest alien to be possible, such that that rectangle lies completely within the histogram. It can maximum touch the histogram at some boundaries or maybe some sub part of the boundaries. Okay, so now let us analyze it. Let us analyze it a bit. If a histogram, let us analyze what our answers can be. If a histogram starts somewhere, suppose it starts somewhere in the middle of a block. That is, I have this x coordinate, I have this another x coordinate, I'm starting somewhere in the middle. So what can we say? If I start somewhere in the middle, and whatever I stretch it up to, can I say that we can easily stretch it towards the left? Right? So definitely it does not make any sense if we partially cover a block, because for the rest of the block I know whatever height I'm maintaining for this rectangle, it may be even less. It may be something over here as well. Suppose I'm maintaining something over here. So whatever height I'm maintaining, I know that the same thing I can continue to this left margin. This will always happen. I know this. So when I do continue this, definitely I won't be changing the height. I won't be bound to decrease the height, but I can easily increase the width. So definitely there is no sense of taking partial rectangles or partial units in terms of width. This is the first observation. So if we are covering from, or if we are starting from somewhere between x1 and x2, where x1 and x2 are consecutive coordinates, then definitely that does not make sense. We can stretch it to x1. So what shall we say? That it will always start on some integer value. It will always start at some integer value from where some bar is starting. So where this bar is actually starting, we'll always start somewhere from here or somewhere from here, something like that. Similar goes for the end as well. I can say if I have a rectangle which goes up to here, whatever it is, and I stop over here, I can say I can easily stretch it over here. So it does not make any sense to compromise this part, because I don't have to change my height. I'll keep my height the same, the breadth will increase, and the area will be more. So this tells me that to find out the maximum area rectangle, my candidates which are important to me are those which start at a certain point where a certain bar is starting, and it will end similarly at a point where some bar is ending, whatever that is. Now I know that there are many bars from which we can start the rectangle, many bars where we can end the rectangle. We know there are many choices, but the first thing is that these are our candidates. We have to choose between them. Similarly, can we say something like this, that if we are covering, suppose, this particular part from a certain x1 to some certain x2, and I see that we are having something like this. We have a transition upward from here, we have some transition like this, we have something like this, we have something like this, and so on. We have something like this. So can we say that among this, if we have made up our mind that we are going to start from here and we are going to end up to here in terms of the x coordinate, can we say that this should be our only choice? That is, the y coordinate should match with the minimum y coordinate of all these blocks, can we say? So basically they will have their own y coordinates. And I know if I keep this y coordinate, if I choose this y coordinate, then this guy won't be happy. This guy won't be happy, because they will see that the rectangle is outside their level. The rectangle is not inside the histogram. So they will definitely not like it. So from here we can say that whatever this height is, you have to keep it below this h1, you have to keep it below this h2, you have to keep it below this h3, and so on. So if you call this as h1, h2 and h3 and h4 and h5, you can say that whatever your height of the rectangle will be, h rect, that will basically be the minimum of, or we can say this has to be less than equal to all of h1, h2, h3, h4, h5, which basically means it has to be less than equal to minimum of h1, h2, h3, h4, h5. Makes sense? So it has to be somewhere less than equal to this. What this indicates is that once we have chosen where we are starting and where we are ending, we know what is our limit. And when we know what is our limit, we know that choosing the maximum value is going to give us the maximum answer. So choosing the maximum value of h rect and adhering to the condition that we will start at x1 and end at x2, we are going to get the maximum area possible for this particular constraint, which is nothing but del x. That is the distance you will have between these, multiplied by h rect, which will basically be the minimum of this value. So this particular h will basically have something like this, that if you keep something greater than this, if you try to keep something greater than this, then unfortunately that will not obey the condition that it has to stay within the histogram. And if you keep something lesser than this, that will waste an area. How? It will look something like this. It will basically pass through somewhere over here. You will say, since it is lesser than the minimum, so this space is unnecessarily wasted. You can easily add this space over here, and this will lead to an increase in height without any change in width, which means an increase in area. So definitely it makes sense that for the maximum area possible, we should follow the maximum height which is possible, which is nothing but the minimum height which is present in this particular range. Makes sense? Well, now you can think about it that okay, so in every range, if I've got the minimum value, then I can directly print the answer from there. The first thing is that you can again relate to my previous video where we talked about maximal, I think it was sliding window maximum. But one observation first of all is that the window was of fixed size. So if the window was of fixed size, it was pretty a different question. It was pretty much a different question. If the window is of fixed size, you can find out the maximum of all the windows in order n time. But if the windows are varying, you can say that not only the windows are of size 3, which are propagating like this, 3 and then over here 3 and so on, but they can be of different sizes as well. They can be of size 1 as well, they can be of size 5 as well, and anything. So from here we actually get that is not a good strategy. Also, let us think that we have got the answers. Let us think that, okay, from I to j, I will give you the maximum height. From I to j, I'm going to give you the maximum height which you can have. Okay, maximum height means in that range, whatever height will be minimum, that is the maximum for you that you can obtain in that range. So I will tell you that, okay, I'll give you the maximum height. Can you tell me the rest of the thing? Then what will be the complexity? The complexity will go something like this. The first thing is, suppose that, okay, we will discuss what if I don't give you the height, but first let us discuss what if I give you the height. If I give you the heights for all these ij, you can say that the number of ij pairs is going to be how much? Number of ij pairs is going to be for I equals to 0, suppose it is 0 index, this is n minus 1. So there are n bars in total. So we can say, I'll choose the red color. We can say that for I equals to 0, j can go from 0 to n minus 1. So we'll have basically something like this. Summation I equals to 0 to n minus 1, and for each we will have j equals to I to n minus 1, and we'll be adding 1. So we can say it will be something like this: n plus n minus 1 plus dot 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 up to 1. So it basically is n into n plus 1 by 2, which is order n square, right? So we are getting order n square pairs, which is quite too much. What if I say that I won't give you the height? What can you tell me? You can again say that I'll choose a similar strategy. Now this is also like pertinent to your interview discussions with your interviewer. If the interviewer says that no, I will not give you the heights, but I want to find you for all the ij, what is the time complexity will take? You can say that, okay, I'll start from 0. I'll be taking up to 1. I'll find out the minimum height up to here. Then I'll proceed one step. I'll find the minimum height up to here. You can go on like this, and from 0 to n minus 1, choosing all of these things for a certain I will take again the same time, order n. What I mean by this is that for a certain I, if you have to calculate all j in succession, you can go on storing the min, and then you don't have to really worry about calculating the mean every time. So when I say you know the minimum for ij interval, finding the interval from I to j plus 1 is going to be very easy. Whatever you know is the minimum for up to ij, you can just update the minimum, taking into consideration the current height at j plus 1. So by that you'll be able to do. So without applying any extra intelligence or strategy, you can find out the answer in order n square. And this is where the trick actually starts. Now it will be somewhere important for us to bring it down to from order n square to order some better complexity, because the interviewer shall be very interested to give you this kind of a constraint and say that you need to finish this in 1 second. Or maybe, as people who are not that much into computer programming, they usually practice, they will just ask you that can we do better. So there's a constant question which I also mentioned in my previous video. There's a constant question which is awaiting you, that can we do better. You shall hardly get any extra hint. Okay, you might not get this, but okay, for the time being, think about it, that if I give you this constraint, what is the algorithm that you can come up with? The first thing is, if you think in this manner, if you think in this direction, that I'm going to consider for all I and all j, you can see there is nothing to optimize. The number of ij pairs are ordered in square. So there is simply nothing to optimize over here in this approach. In the previous problem, which was sliding window maximum, we had talked about first improving it to n log n, then improving it to n. But in this case, we really can't do anything, because the moment we have fixed the pairs, the moment we have fixed our possibilities, we already have order 1 for each possibility. We can't do anything better. So it doesn't make any sense. Hence, what is the different thing we can do? We can do something like this, that देखने का नजरिया बदल देते हैं. Let us just change the way we are observing the problem. We can say that for this entire part, right from here to here, I can say that this is the node which is going to form my height. This is the node which is going to form my height, right? So this height is going to reign over this area, this entire area. This height is going to reign over this entire area. So we can say somewhere this height is also influencing this particular range. This particular range, if you think of this particular range, don't consider this as the y coordinate of the rectangle. I'm just telling you, consider this as I and this as j. You can see the same height is actually forming the bottleneck for us. You cannot increase the height beyond that. So in some way, if we observe this particular element, we can say that so many intervals from this I to this j, from this I to this j, from suppose something like this I to this j, all these intervals are actually being governed by this particular element at the middle. And the idea is that this is the smallest element. When this is the smallest element, there is no influence of other elements in the range. If I tell you that this is a range, I'll not tell you what the height is. I'll just tell you that this is the minimum height, and rest everything that may roam like this, that may roam like this. I will not tell you that. You can tell me that, okay, if you tell me where it is starting, where it is ending, I'll be able to tell you what is the difference, and I'll multiply with this height, because I know the maximum triangle cannot definitely exceed this in height. So this is another way of observing the problem, that if we start from here, if we start from this part, and if I say from where I am, like up to where I'll be important, it will say I'll be important to this particular range because all of them are greater than me. The moment I'll see some guy who will be smaller than me, what will I say? That now my height is no longer important. So this is what we are observing, that for all ij pairs, we can see that there will be this particular stage after which we might get some value which is smaller than this part, which is basically smaller than this particular small interval, and we can say after this whatever we have in this part, no longer this can govern, because it has already got something which is smaller than this. But in this entire part where it knows that I am the smallest, it can directly say, yeah, I will govern what will be your height, and definitely the maximum value can be this particular range multiplied by me. So in this particular range, suppose this is I and this is j, The first one is I, the last one is j. What is this interval? That in this range, all the heights are greater than equal to this particular height, which is at k. So if I say that from I to j this is holding, one thing I can say that if you choose some I dash j dash which will lie inside ij, that is I dash is greater than equal to I and j dash is less than equal to j, for any such I dash j dash we can say that the area is going to be this height, which is the height of k, multiplied by something like a del x. Del x means that same thing, j dash minus I dash plus 1, something like that. So what can we say? That j dash minus I dash will be the maximum when we choose the extremities. We are saying that for any j dash I dash, over here, j dash will be definitely greater than equal to k and I dash will be less than equal to k, of course. So I dash will be less than equal to k and less than equal to j dash. So following this, we can say that any I dash j dash will basically follow this particular kind of formula, which is hk multiplied by j dash minus I dash and maybe plus 1, something like this, okay? So this tells us that when j dash is largest, which means j dash is less than equal to j, so when this is largest and I dash is smallest, I'll be having my best value. And intuitively also right, if we stretch this rectangle to the maximum limit possible, which starts from the leftmost extreme and ends at the rightmost extreme, till which this particular element can dominate, we will say that yeah, it is able to now establish its reign. Nobody else can control the height, only this will control the height. And we can say that, just check that. Now, inside this, if you target anything, if you target any other j dash I dash, then that does not make any sense. That does not make any sense because for this particular middle element, only one thing is important, that to my right, up to where do I have elements who are greater than equal to me. So long as I'll get elements which are greater than equal to me, I can mellifluously go on taking elements into me. I can go on mellifluously including those indices, saying that they will lie within me. Okay, but this does not hold the moment I'll get a smaller element. The moment I get a smaller element, I say that now my period is over. Let us see through this example or through some other, better example, something like this. So again, I'm trying to be very slow so that the intuition is pretty clear to all of you. Why we are doing each and everything. I don't want to haste it over there, just in the interest of time or in the interest of anything else. I'm not speeding it up. Now you can see of something like this. So you can say that if I want this element to be the governing element in a certain range, for any range, we have discussed that definitely it is going to be equal to the minimum height. We know this. It cannot be less than that. We have seen that. Now utilizing that, suppose this is that particular height, hk. So we can say this can go up to here, because up to here you have elements which have height greater than equal to this, and towards the right it can go up to here. So we will say if you choose this as the height, then this is going to be your range. If you rather say that no, I want the height of this guy because he's so so cool, so you can say that I'll basically then look at it that from here up to where can you go. So you can say that no, I can go only up to here. All the elements, the element which is just to my left is so stubborn. He is so less than me and he cannot allow me to continue my height. So he can continue only up to here and he can continue only up to here. That's it. Now you can say that if I choose this particular element, I'll get a better freedom. I can continue up to here and I can continue there up to there. So I can take this entire height. So what is mattering? Now these are the candidates. We can say these are the candidates. For this also, this is alone. It has to stay alone. So we can say that in your maximum area rectangle, either one of them, any one of them at least, will form the minimum height. And I'm saying that take any case, whatever it is. Suppose this one forms a minimum height, then this rectangle should and must continue until the leftmost bar is lesser than this and even to its right. It should not stop before. it should cover this entire area. Okay, now this is the observation, that whichever is your minimum, whichever is going to form your minimum or maybe your governing height, take that as the standard and try to extend as much as possible. So now see, now how many options have we got? We can choose this as that governing bar, we can choose this one, and so on. We have n choices. We have n choices compared to the n square choices that we had in case of the previous methodology we followed. So here we can say that we have got n choices. Great. So now let us see how this helps us. When we have these n choices, for each of these choices, a trivial thing would be something like this. A trivial thing would be something like this. That I less than n, I plus plus, and I'll say whatever you are choosing as the governing bar, you are going to do something like this. For j equals to, I'm assuming that they are all initialized. So j is equal to I minus 1 or something like this. Yeah, j is equal to I minus 1. J is greater than equal to 0. J minus minus, and we will see that if that particular j is, suppose it is less than the current thing, which is ai, then what shall I say? If this particular thing holds, that means I cannot go to that j. So what I'll be trying is, I'm starting from I minus 1, I'll see how many I can accumulate together with me. कितनों को मैं अपने साथ ले सकता हूँ मेरे लेफ्ट में, like starting from just behind me. So whenever I'll see that एक एलिमेंट छोटा हो गया, मैं कह सकता हूँ अभी मैं और एक्सटेंड नहीं कर पाऊंगा. So this is the point where we will break. Break means we are going to break the for loop. So when we come outside, we know that what is basically the bar where I cannot reach. So basically j equal to j plus 1 will tell me the last bar that I can reach. This will tell me the last bar that I can reach. Similarly, I'll do something like this for k equals to I plus 1, k less than n, k plus plus. And I'll say that if ak, the similar thing, if that is less than ai, then you will just break it. Because then from there onwards, it is not important to me. Till the part it was important to me, I have acknowledged it. But now they are not important to me. So what can we say? When we are doing this, we can ensure that now if I do k equals to k minus 1, this means that in the current interval j to k, I can ensure that all the elements are greater than equal to ai. If you see, from I was proceeding to the left, and I proceeded only up to the point where aj is less than equal to ai. Sorry, greater than equal to ai. Similarly, I am ensuring to my right that k I'll be taking only to that point where, up to where ak is greater than equal to ai. So taking that into consideration, I can say something like this, that the maximum area, or to my candidate, what is going to be added? I can say that if I'm storing max area in some variable, I can say I can update that variable in something like this, using something like this, max area comma the height of this ith guy, which is hi, or I think ai is basically the value, ai multiplied by k minus j plus 1, right? Because I know this is my last element, this is my first element, so this will tell me the number of elements in that range, right? So this is the pseudocode or C++ code or Java code, whatever you say. Yeah. So this is going to look like something like this. So I can say that for all the middle elements, what this indicates is a particular middle element. What this indicates is a particular middle element. So I can say for all the middle elements, I am checking what can be the maximum area it can handle. And this is basically that maximum area for a particular I. For a particular I, it is finding out the correct value of j and the correct value of k. And here they are forming basically, once they have seen the first invalid, they are automatically incrementing 1 or decrementing 1 to find out the last one which is valid. So that gives us these expressions and we can maximize it thereby. Okay. So just to summarize, all that we are doing is choose the first element as the minimum height rectangle, see how far you can go. Choose the second bar as the minimum height and see how far you can go. And this continues till the end. And I can see that for all of them, in total, this is likely to take around n squared time. I don't know how far this will really, let me proceed, but it's quite likely that this can take up to order n. This entire thing inside this I, this is likely to take up to order n because I'm starting from 0 and I'm ending at n, so it can easily go up to order n. I'm starting I'm starting from basically I minus 1 to 0 and I'm going from I plus 1 to n. So I'm basically almost covering the entire range from 0 to n. If it breaks, that is a different thing. But this tells us that the whole algorithm basically comes out to order n square. Due to the multiple multiple values that I is going to take, this will be order n square in total. So now we'll be improving on it. Let's see how we can do that. The first thing is that for this guy, suppose for this particular guy, what I observe is that in front of me somebody greater than me is coming, right? So I can say something that before searching for my own smaller element who will be on my right, why don't I search for this guy? Suppose this is A and this bar is B. So A अपने right में, to its right, A is searching for the lowest height element or for a lower height element. A is searching for the first element which is lower than it. और यहाँ से उसके जगह उसको मिल गया B which is higher than it, which is greater than it. So what will it say? That let B find it out first, because अगर B से कोई छोटा होगा तभी मतलब बनेगा मुझे देखने में. If B gets something which is smaller than B, then only I can compare myself to that. Because if something is smaller than me, it must be smaller than B also. If something is smaller than A, like this one, this must be smaller than B, whatever it is. Okay, उल्टा हो सकता है कि in front of A you have B like this, and there is something smaller than B which is not smaller than A. So you are saying that okay, B will find his successor faster. If B finds something, then I'll then see. Okay, if B is finding something, I'll try to see if I can utilize that. But first of all, let me put B at the forefront. B requires a successor. At the same time, suppose now B has got a successor like this. What can you say? That now, when you have got something like this, suppose this is C, B has got its successor, you can say now forget about B. B has got what is its next smaller element. B has got it, so just forget about it. At the time being, we are considering only elements on the right. हमें सारे elements के लिए निकालना है कि इसके right में कितने सारे, like हर एक के right में कौन सा immediately छोटा element है. Something like this. That suppose you have got some heights like this: 5, 7, 6, 8, 4, 3, 9, 6, something like this. So for all these guys, we are searching which is the next small element, next smaller element. Now we are looking at it in this way, that we have 5 which is waiting, which still doesn't have. Now we have something like 7 which says I am greater than you. So please allow me to check this first. If I find something which is smaller than me, then only फिर ही तुम्हारा chance बनता है. Then only it's an opportunity for you. If something is greater than me or greater than equal to me, it is nothing to you. Like it is not at all important to you. So please allow me to search for myself, to try for myself. So this is what it starts with. And it says that okay, I'll take the position now and I'll check with myself. Next it faces 6. So when it faces 6, it is going to say that okay, I found my smaller element. So my smaller element is going to be 6. And I am releasing myself. Now I am not at all important. I have found my next smaller element. And I know that mere piche, behind me, no one's, like I am not the smaller element for any one of them. I know this. So this is some idea that it applies, and it says that okay, now let's allow 5 to now apply. Allow 5 to try. So it will allow 5 to try. It will say that I am moving away. Try yourself. So 5 can say no, I am not greater than 6. So it will ask us that 6, you sit in front of me. If you find something smaller than you, then we can try, as there is no meaning for me to try. If you find something smaller than yourself in front of you, then only I can try with that. So 6 sits in front, and 6 will say that okay, let me see now. So 6 has not yet got. Now it has got 8. 8 says that I can't help you. I'm not the smaller element. So what are we searching for? We are searching for the next smaller element for all these guys. Next smaller element. Okay. And 6 says that okay, 8 is not next smaller, but 8 will find its next smaller either before me or at the same time as me. So let me just keep it in front. Now let us see what it will do. Now 4 is going to come. 4 is going to come and say, oh, I'm smaller than you. 8 is going to say, wow, so I've got my successor. I've got that after me, 4 is going to come. This is my next smaller element. So 8 will simply release itself and allow 6 to look at it. 6 will say that, yeah, 4 is smaller than me. So over here you can see that 6, the task of 6 is not getting delayed. 8 says that 4 is smaller than me, then only it makes sense for 6 to check with it. So over here you can see that we are not checking whether 8 is smaller than 5. Why? Because 8 was not smaller than 6. So it was not at all essential to check whether 8 is smaller than 5. 6 is making the task easy for us over here. Similarly, over here 8 made it easy. 8 said that okay, I found 4, now you test with 6. So 6 says that yeah, I am also greater than 4. So I have also got my successor. My successor is also going to be 4. Now 4 can sit at my place. Now 5 stares at it. That okay, I have got something now, and it says 4 on the plate. It says yeah. Now I can also leave this data structure. I will allow 5, like I've got my element. Now whatever 4 wants to do, let that do. I have got my next smaller element. Now we have 4 and there is no other element, so we can just place 4 over here. 4 is still waiting for its next smaller element. 3 comes, 4 says I've got my man. So it gets 3, 4 removes herself. And now there is 3 over there. So 3 will just enter because there is no one else looking forward to see 3. There is no one else waiting for 3. Then 9 comes. 9 says that okay, please wait a bit. Let me spend my time over here. Whatever smaller element I'll find, that might be a smaller element too. If something is not smaller than me, don't waste your time checking with that. So I'm going to do this task, make this task easier for you. Now 6 comes and it says that okay, I'll remove myself because I've got my man. I've got 6. And then 6 can introduce herself and over here, or 6 can introduce himself, and 3 says that 6 cannot help 3 get its element. So we say that after 3, basically, there is no smaller element. There is no smaller element, but we can say that after this, if we say that there is an imaginary 0, like in our case of histogram, after the last bar, what do we know? There is a bar of height 0, something like that. So if you have something of height 0, we can say that all these which are remaining, which don't have anything to follow them, they can easily consider them to be of height 0. So after this, there is a 0th element which is just following them. Makes sense? Okay. So what do you find over here? We are only doing operations at the end. So you see, when the data structure was something like this, 5, 7, we were only concerned with the last element. Only when we are removing it, 5 becomes important. So what kind of data structure or what kind of implementation does this spark in your mind? This brings to our mind the data structure, very popular data structure, stack. What stack allows us to do is that it will basically keep on placing these elements over here, basically 5 first, then you will have 7. Then when 6 comes, it will say just get lost, you have got your element. It will introduce 6, 5 will say yeah, sit in front of me. You place 8 over here, then 8 is going to say okay, my time is over. 6 also says I have found 4, my time is over. 5 tells my time is over because I found 4, and so on. So you can have multiple, like, all these operations. The important thing is that for finding the smaller elements of all these positions, how much total time am I taking? So can we see what are the operations we are doing? We are doing comparisons, but before doing comparisons, what are we doing? Suppose this is our stack or this is our data structure. We have some elements over here. So when we are bringing something, some x, what can we say? That this element will either stay here and allow x to introduce itself, allow x to come and sit in front of him, or this will pop out itself. So definitely with every comparison, something is taking place. After every comparison, either some push operation is taking place or some pop operation is taking place. So with every comparison, some push operation is taking place. I'm sorry. So either one push operation is taking place or one pop operation is taking place. Does this make sense? Okay. So let us not count the comparisons. Let us only see how many pushes and how many pops are taking place. Okay. So every comparison I know that is associated with one push or pop operation. Why? Because the moment I see that this element x that I'm introducing, this is smaller, I will say that pop it out. I'll say pop it out. And if I see that this is greater than equal, this is greater than equal to that element, I will say that introduce it. Introduce yourself. So this is basically the idea. Every comparison is basically one push or one pop operation. And now what is the number of push operations? Every element you can see it is pushed only once. It is pushed only once because it has to find its next smaller element. So once it sits in the stack, nobody is going to remove it till it finds a smaller element. So it will be introduced in the stack only once. Every element, first thing is introduced in stack exactly once. Introduced into the stack or into that data structure exactly once. So we can say for every element there is exactly one push operation associated. And we can say that it will be popped out exactly once. Why? If this element turns out to be smaller than it, then this will be popped out. So if some element happens to be smaller, it will immediately get popped out. And if it does not happen to be smaller, it will not get popped out, it will wait for it. But once it gets popped out, it will never re-enter the stack. It is not going to come again into the stack, or it is not going to be popped multiple times. Once popped out means over. You have found its element, over. So it is going to be popped out exactly once. Okay. So if we can implement this, then it's well and good. We'll get all the next smaller elements. Similarly, can we say if I just move in the previous direction, can I get the previous smaller element like this? If I go in the previous direction, if I start from the last of the array, suppose this particular array 5, 7, 6, 8, 4, 3, 9, 8, 9, 6. 5, 7, 6, 8, 4, 3, 9, 6. I hope this is the array. 5, 7, 6, 8, 4, 3, 9, 6. 5, 7, 6, 8, 4, 3, 9, 6. I know 0 is over here, 0 is over here, and I don't care for them. I will only take them as reference if needed. I will say for this guy, I don't know what is the element waiting for me. What is the element which is my previous smaller? So I am going to search for previous smaller element and we will see whether we can do that. Previous smaller element. We can do something like this, that we will place 6 over here. Next time we'll be placing 9. If we place 9 over here, okay, when 9 will be introduced, it will first ask. 6 will see whether 9 is smaller than it. If it is smaller than it, it will pop out itself. But it sees that 9 is greater than it. Again, the same logic. 9 will find its predecessor much before me. So let 9 stay over here. Similarly, what do we observe now? Now 9 will find 3 over here. So 9 will say, okay, I found my successor or predecessor, whatever you say, it is 3. So it will emit itself. 6 is going to check. Now 6 has also found it. It is 3. So it says it is 3. Pops out, and now 3 is going to enter at the end. Now when 4 comes, it says that okay, 4 is not smaller than me, so let it introduce itself. Now 8 comes, 8 also says it is smaller than me. Now you get 6. So again you can observe. When 6 comes, you can again see the same thing. Let me change the color. You can again see the same thing, that 6 is not smaller than 4 and 3, and hence the decision was right. 6 is smaller than 8. So definitely the smaller element shall come for the greater element. So among these three numbers, definitely after this, the smaller element will be first coming for 8 and then for 4 and 3. It may be at the same time, maybe later. So over here, exactly that is happening. So 8 plus, I have taken the correct decision to keep myself at the front. I will easily pop myself out and make the task easier. So I've got 6. Now 6 says that okay, I am not smaller than you, so I'll stay in front of you. Now you have 7. 7 also says that yeah, I'm not smaller, so I'll keep myself in front of you. 5 comes and says that okay, I'm smaller, so you can leave. 7 gets its man first. It gets 5. Now the point of the turn of 6. 6 says that yeah, I've got you, so I've got 5. And now 4 says that still I'm not able to get. So 5 introduces itself and there is no one else to take care of. You have only 0. So all of them will basically have 0. This also you can do in this order. 5 is first going to take 0 and going to pop out. 4 is going to take 0 and then pop out. 3 is going to take 0 and then pop out. These are the previous smaller elements. Make sense? Cool. So if these two things we do, in the similar fashion we can see the same properties hold as we have discussed over here, and hence the entire algorithm will run in order n time. Why? Because there are n elements. There are n elements. Every element, you are basically dealing order 1 operation over here and order 1 operation over here. So there is exactly order n operation taking place in this entire usage of this stack. Makes sense? Over here also exactly order n operations are involved. So you can say for large numbers we can easily execute this, and by this what shall we be able to find? For every position in the histogram, for every position, let me now summarize it, why we discussed all these things. If we have a histogram something like this, however basically we have this, we can say for every position I will know what is my next smaller element, what is my previous smaller element. When I get this range, I can say del x into h is going to be the maximum area possible for this particular part, for this particular smaller height. Similarly, I can say that for this guy as the smallest element, this is going to be the range which is important to me. So I can find out the next smaller element which is over here, the previous smaller element over here. I can find out the range which is between them and I can calculate something like this. So if I find this index is something like suppose it is k and this is j, I can say that from j plus 1 to k minus 1 matters to me. So I'll do something like this, k minus j minus 1 multiplied by h. Makes sense? I just excluded those two elements. That is why there is a minus 1 over here. K minus j plus 1 minus 1 minus 1. That is why k minus j minus 1. So this is the idea. So now I am checking for all the elements and I am able to find out all these values for all those elements. I'll just find out what is the maximum among all those values, right? I can just find out what is the maximum among all those values. So that's it. Let's quickly look at the implementation. Then we'll try out some sample test cases. And if it passes, well and good. But keep these intuitions in mind and keep in mind how we approach this. What is going to happen if after, suppose this is the guy whom I want to keep and this is 7. What will happen if I get a 7 over here? If I get everything greater and all those, suppose I get something greater over here, something more greater and so on. Here I get something exactly equal to 7. Suppose this height is 7. I should keep it, right? I should extend it beyond this. I should extend it beyond this. Something like this. I should extend it beyond this. Because it allows me to maintain my height. I am not being debarred from dominating. So definitely, I will say, yeah, allow me to continue. Even here, I'll say, allow me to continue. Even if you see 7, allow me to continue. But if you see 6, 5, 4, 3, anything like that, smaller than me, then stop me right over there. So that's basically the idea. Are we repeating? Will these duplications cost me? No. The the smaller, next smaller element, the previous smaller element, they will calculate and give me all the values in order n time. Then I'll just pick up the values. I'll have all the values. Suppose for this I, for a certain I index, the next greater array gives me j, and the next smaller array. So I've taken the next smaller elements for all. So the next smaller array, suppose this gives me j over there and k over here. I can simply say that just do this kind of computation. So it does not take me any extra effort if there are duplicates. I just need to keep in mind when I'm forming the stack, that time I need to keep in mind that if an element faces the same element, he should not pop out itself in joy that I found something as good as me. I have to find something smaller in me because I want to wait. Every element wants to wait. He wants to wait so that he can see as many elements as possible because they want to maximize the area. Okay, cool. So let us quickly look at the implementation. I hope the screen is visible. And okay, so CD, I'm sorry, competitive programming lectures, and suppose let us copy sliding window maximum, which I had shown the previous. It's not here. Okay, I think in interview problems, CD interview problems, CP sliding window maximum. I'll be copying this to this particular file. Let this be greatest maximum area rectangle. Okay, dot cpp. Now let us see how we can code it fast. We'll have something like this, and okay, so this will basically tell me the heights. So let us say I'm storing the heights over here. I'll be removing all these things. Okay, so I'm storing the heights now. Now I'll be finding the next smaller elements. So I'll first of all form two vectors, vector ll, next smaller. I'll again have n comma 0, and then I'll have suppose I keep minus minus 1. At the end everything will be filled up, no worries. I'm sorry, previous smaller, so prev smaller. Okay, and now what shall we say? First of all, row from I equal to 0, I less than and I plus plus. And now I'll require the help of certain syntaxes. I hope I can correctly write them. Stack ll something, name it anything, stack ll st. And now while we are introducing some element, if we see that that element is lesser than me, then I'll pop out whatever is there in the at the top of the stack. So while st dot empty, I hope it's something like this, else we are going to check it later on. St dot top, I guess this is how it's written in C++, and I'll be storing the indices. Okay, let us store the indices. So if I see that a st dot top, this is greater than the new element that we are introducing, then we will say that next smaller of st dot top is going to be equal to I, and I'll say st dot pop because I need the indices. So I'm storing that indices, that this is the next smaller element I've got. Now I'm going to say that okay, all those things are over. Now let me enter st dot push. I think push is the function. I'll have I over here. Now when I know that I've not found any next smaller element, what can I say? Just reach the end of the array, that is n. Up to n minus 1 I have got all these bars, and if everything in front of me is greater than me, I'll choose up to n. N is basically my limit. So I can say something like this, that while st dot empty, this is not true, I'll do something like this, ll X is going to be st dot top, and we can say next smaller x is going to be what, n. You can say something like this. Good. So see how I'm labeling this. Even this naming actually matters, and you can name this as height, you can name this as number of elements, because the naming matters in the industry. So please try to keep this in mind, because there are many companies, even like sharing my own experiences or some experiences that I had heard of. Many companies eliminate people due to wrong naming. So just the way I've named these two, you can name even H and N. It will improve your chances of being selected. Cool. So now let us do just the opposite thing. We'll do exactly the opposite thing. Before that, do you want me to check? So let us check if all these next smaller elements are coming correctly. So let us say it is, we are printing, suppose, next smaller element. So let's print something like this, next smaller. I'm going to print the next smaller index, okay? Or let us print a of next smaller that index. Oh no, we'll face an error. So let us print only this. G++ maximum area rectangle. So now suppose, okay, undeclared identifier, I think LL. So over here LL is missing. That's the only thing. Yeah. Uh, A is not there. What is there? H is there. So I need to correct it now. H. This is also H. There you have got, yeah. Now it should be fine. Dot slash a dot out. Suppose there are 5 elements, and suppose we pick up these 5 elements. So the first 5 elements, 5 7 6 8 4. So you have 5 5 7 6 8 4. Have we missed anything? No. So there is some infinite loop which might be happening. Okay. So the infinite loop occurs over here. We are not popping it, right? So we should pop it over here. So when we pop it, now it should be seamlessly working. Well, too many things. I think I copied the code right away. Yeah, so it has to be 5. It has to be something like what? 6 oh 5 7 8 6 8 4. 5 7 6 8 4. So we can see for 5 the fourth index is smaller, which is 4 basically. For 7, just the second one, which is 6. Index 2, right? Index 2. For 6, again 4, which is located over here. So 4. 4, there is this one. And 8 also says that, yeah, this is the guy. So you have 4. And 4 will say that nothing inside the array, only 5. It will say something like this. So pretty much, deterministic. Let us now do the simple thing. We will do for previous smaller now. So stack is empty. We know that now stack is empty, so I can reuse the stack. You can also name the stack in better ways. You can name 2 different stacks for it. That can improve your chances. We'll have something like this, I greater than I minus minus, and we'll do the same thing. Nothing different. Just prev smaller. Okay. And over here also prev smaller, and in this case minus 1. Why? Because nothing within the array is smaller than this, so minus 1. Anything else can you see that we need to change? I don't think. Yeah, it seems fine to me. Greater than hi, yeah, it has to be greater than hi. Okay, so now what can we say? Simple. For I equals 0, I less than n, I plus plus. Again, LL I'll be missing and I'll be getting a bad error. So okay, LL area is equal to 0. This is the max area. So what will you say? Area equals to max of area, comma, whatever is that element, whatever is the height of that element, suppose hi, this is the height of that element, we'll multiply it with next smaller, whatever is that index of next smaller, minus prev smaller I minus 1. We'll find this. and we'll basically see out this particular area. Okay, so let us take certain examples. We have 57684396, 57684396. We have 24. Let us see what are the things we can form. First of all, let us see from here. That let us at every step let us print whatever you're getting, choosing that particular thing as the middle element. You can say we'll be getting something like endl. Okay, so you can see that if I choose 5 as the middle element, I can proceed up to 8. So it will be 5 multiplied by 4, 20. That is why I'm getting 20 over here. This is 5 multiplied by 4. Next, if I choose 7, I cannot proceed rightward, I cannot proceed leftward. I can only stay at my position. If 7 is the minimum height, I can only stay in my position. So it is 7 over here. Similarly, if I have 6 as my minimum element, then I'll be basically proceeding from 7 to 8. So there are 3 elements in which I can have the height as 6. So it says that 6 into 3, 18 is the height that it contributes. Then I'll see that using 8, what can I go? I can only have this element, so it is only 8. For 4, I can say I can start from 5 and I can reach up to 4. So it is again 5 elements, 5 times 4 is 20. Now with 3, let us see. We can start from here, we can go up to the end. All the elements we can cover using this 3 because 3 is the smallest height. But it is not always the case that the smallest height is going to guide you. No, we can prove it differently. So 3 is going to guide you in this case. It is giving you 24. Similarly, 9 tells you that I can take only myself, and 6 will tell you I can take only 6 and 9. So 6 into 2 is 12. We can take a different case just for showing that only the minimum height may not help. So suppose it is 8, 8, 8, 8, and suppose it is 3. 3 8s are 24 and 8 4s are 32. So you'll see 32 will be the answer in this case. And for 32, you can see that we basically need these 4 to be together. Okay? And hence this is the governing height. It chooses 8. Clear? So fine. If you want, we can generate 10 to the power 5 numbers, and we can check with that how quick it will finish. Let us try to do it. Suppose touch something like drum.py. Okay, using a Python code, I'll be quickly trying this. That suppose import random, and now I'll be carrying a list. lis equals to 0 means nothing, and then for I in range 1 0 0 0 0, there is 1 2 3 4. Suppose let's choose another one. lis.append some random number. Okay, so let us choose random dot randint, and let us choose 1 2 1 2 3 4 5 6 7, these numbers. Okay, yeah, now we will copy this. Yeah, so we will write something like this, or we can say something like this. Suppose let's form a string s equals to 1 2 3 4 5 slash n, and then we'll be doing something like this: s plus equals to this. Okay, now we will say that with open input dot file, input comma in writable format as f dot write lines s. So what will I get it? Once I found this, python 3 prog.py not okay str, yeah, then we can say dot slash, or what can we say, yeah. Now I have basically stored this in input, so I've got a file input, and you can see a very long okay, so I've not added spaces between them, so I should be adding spaces, so you have something like this. Okay, now it will look perfect. So you can see that they are all specified integers. Let us increase this as well. Let us use this as 2 and this also as 2. So we will have a very large test case over here, and we will run this. So let's see, g++ input. I'm not sure how it exactly, where it prints it, but it should have been able to print it. Maybe we can write it something like this: to output. Okay, so we have got some output. It's not printing anything. That's strange. So usually I keep on doing these things in Java, but okay, I'm sorry, this is my mistake, I'm sorry. So we have solved this. Now basically what we need to do is dot slash out, and there we need to push input, and now we can see that we are going to get the output. Okay, so there are so many numbers, so we'll not print all the numbers. We'll only say that don't print these numbers, print only, I'm sorry for all those things, yeah. Now we can see only the output we are going to get in a fairly small amount of time. So there are so many numbers, yet we are able to get in quite a small amount of time. Makes sense? That means it is not running in n square, it is running in order n. Else you would not have been able to get so fast. And you can say that, okay, we can increase it to 50,000. It won't matter much. It will just take 5 times the time. So yeah, you are able to get something like this. Is this the same thing? That is strange. So maybe I'll okay, let us reduce this. It might get confused due to all these things because they are large numbers. Okay, I have not run the program. I'm sorry, I didn't run the program. Yeah, python prog.py, and now I'll be running this, and there you go. Now you'll see that even in this case the output will come pretty fast. Okay, that's it. So this is a very important problem. Go through the recording, go through the video as many times as you would like to revise it. Take care and do subscribe to the channel, and let us know what videos we should bring forward for you. I am trying to keep the pace low so that it can be understandable to most of you. And yet then if you have any suggestions, please let us know about it. I'll be informed by the team, or I'll myself look at the comments, however. So this is a series which you have started, and we wish to have you till the end of the series. So take care, and yeah, good night. Bye.